Hello everyone to the afternoon session of the first CVPR workshops where you don't need your shoes. So without further ado, our next keynote is Jitendra Malik. We all know him, he doesn't need any introductions, but I will try to summarize. He is now in Fair and Bayer in Berkeley and Facebook. And he is recipient of numerous awards for all his foundational research and all of his contributions to the 3D fields for humans and objects and scenes and everything you can think of to digitize this world. So today he will talk about learning to see people and objects in 3D. And please, Professor Malik, the stage is yours. Thank you.
Thank you very much. So good morning, good afternoon, good evening, depending on whichever time zone you are in. It's unfortunate that we all have to meet virtually rather than in person, but I like to try to make this as real as possible. So therefore, it's a live talk, and of course, at the end of it, we'll have time for questions. So just to verify, can you see my slides clearly, which says learning to see people and objects in 3D? And can you hear me? Excellent. Thank you. Okay, so this is a 1-hour talk, and I'll try to keep the talk part to 45 minutes, and then we'll have 15 minutes for questions. So let's see, what are we talking about? So actually, at a CVPR workshop 8 years ago, I gave a talk where I tried to talk about all of computer vision in a somewhat grand way. And I said that the problems in computer vision can fall into 3 categories: recognition, reconstruction, and reorganization. So recognition is about assigning labels, chair, dog, etc. Reconstruction we can think of as inferring properties of the 3D world, largely physical and geometric. So shape, depth, surface normals, reflectance properties, lighting, etc. And reorganization refers to, it's from perceptual organization, which sometimes people would call grouping or segmentation. And my point was that these 3 processes are actually all interlinked, even though they have been studied separately. And that we should in fact study them together, and that there are these bidirectional links. So the information flows back and forth between these processes. So this was before deep learning had actually taken off. But it turns out that the deep learning framework actually makes all this so much easier, because in a network, it's much easier. It's a uniform architecture in which one can do multiple of these processes at the same time. And as an example of the linkage where it's really complete and well done is the linkage between recognition and reorganization. And I'm going to take as example the work on mask R-CNN, and this itself is a culmination of a long line of work. And what you see here is what we can do today. So we can detect objects, we can put bounding boxes around them, we can mark their pixels. And these are very impressive results. I mean, in 2012, when I was talking about the 3 Rs, I could not have imagined that the results would be of this quality. And here is yet another example. And of course, at this conference, we're going to see lots more developments on this theme. But what's missing here? What's missing here is that this is 2D flatland. We have pixels, but these are all like pixels in a plane, the image plane. What we really want is objects with 3D shape arranged in a 3-dimensional spatial layout, because that's what the real world is about. And some of our understanding of an image is not complete until we have captured that. So here, when we have some object hiding another object, some object occluding another object, it all appears like an interruption of the pixel mask. Whereas in 3D, it's actually very simple, right? You've got some object in front of another object, so it occludes it, right? So that's the kind of stuff we want to interpret and see. So that's the 3-dimensionality that we want to capture. And suddenly, a lot more of this stuff will make more sense. So the future is seeing in 3D, and we have moved from detecting boxes to detecting masks. And now, of course, We are in the early days, I would say, of 3D shape. So let me recap a little bit by at the very big picture of what has been done in 3D in computer vision in the last 60 years, because the early work in computer vision is in the 1960s. So in the last 60 years, we've been working on computer vision broadly, but of course on 3D vision. And here are, I think, two main tracks of that line of work. The first track actually began with Larry Roberts' thesis, which is considered the first PhD thesis in computer vision, top left, the blocks world. So the idea is that we're looking at a single image, but that image is the projection of some object in a 3D world. In this case, it's a cuboid, a rectangular cuboid, and a prism. So what we do when we see the image is that we don't just see it as an image. We see, there was some 3D object which gave rise to it, and I have a list of 3D objects, so I can interpret this. Now, the idea can be carried forward from simple geometric shapes to more complex shapes like faces. So what I have on the top right is what's called the area of morphable models. And in the context of faces, Blanz and Vetter have a famous paper from like 99 or something like that, which developed this idea. So even from a single image, we can guess what the 3D shape is, because the space of face shapes is not arbitrary. There is a systematic structure there. So from a single image, we can get a good guess of which point in the manifold of face shapes to pick. The bottom row has a different tradition, and this tradition does not rely on having object models or specific knowledge of particular objects we are looking at. So we can look at the shading pattern, that shape from shading work from Horn in the 70s, and structure from motion, which is the idea of the information available from multiple views. And it could be stereo, it could be structure from motion, it could be really ideas going back to the 19th century and photogrammetry. So these are much more generic techniques. I don't need to have seen that object in advance. So I would argue that 3D in computer vision, whatever be the technique du jour, like today we are trying to exploit deep learning, has to have these two flavors to this work. And I'm going to try today to use sort of deep learning techniques, but at the top level, these are the two main tracks that we are trying to pursue. Okay, so I'm going to start with the first track, which is essentially exploiting knowledge or prior experience with objects I've seen before. So in that previous slide, it was like cuboids or faces. So this is work, Mesh R-CNN. It was presented at ICCV last year. And let me go through the basic idea here. So this is going to be a setup like this. So we are given an input image. We want to get to 3D meshes. How do we do this? We can do the usual stuff, 2D object recognition, put a bounding box around a sofa or a chair or what have you, and mark the pixels. We can even do better than that. We can get 3D voxels. So think of this as like little Lego cubes, and we have assembled the object with those cubes. Now, there's a fundamental limit to using voxels, which is that we can't have higher spatial resolution if we use uniform voxels. Why? Because the complexity blows up as a cube. So 32 cubed is already pretty big. 64 cubed is getting much bigger. And at some point, you just run into limits of memory and so forth. So meshes are much better because essentially meshes are only representing the surface of the object. So basically, you're down one in dimensionality, right? 2D versus 3D. So that's a big win. And what we're going to do is an approach which starts from the pixels to voxels to meshes. How do we do this? So this is the pipeline. So the pipeline starts with an image, and it's constructed as a modification of the R-CNN pipeline. So the R-CNN pipeline, which enables, for example, mask R-CNN to work, we're going to modify it a bit, and now we're going to spit out meshes. And this is a supervised learning problem. So we assume that suppose we are trying to take this chair which is what you see in the image, and we want to return the mesh of a chair, we are given as at training time, we are given images of chairs and meshes of chairs. Both are given to us at training time. So it's a supervised XY, XI, YI kind of setup. How do we do this? So we start with the image where there's a box mask branch, standard stuff. But then there's a branch which predicts voxels. Okay, and that's where we get this output of a cubified mesh. So this is not very good. The resolution is quite kind of poor. It looks very blocky. But the nice part is that it's simple and general. Voxels have that nice advantage there. The advantage comes shows up, for example, that we don't need to know the genus of the object in advance. Is it the homeomorphic to a sphere or is it homeomorphic to a donut? No problem. The voxel prediction will work fine. Okay, now we want to get to a nice mesh. Okay, how do I do this? So what we do is we take this cubified mesh. It's crude. It's very approximate, and we need to clean it up. How are we going to clean it up? For every vertex of the mesh, we want to get a feature vector. The feature vector essentially comes from the pixels, or rather the pixels after several layers of a ConNet have worked on it. So that's this vert align stage, which is attaching to vertices of the mesh feature vectors which are descriptive of the image content, the pixel content. And now what we are going to do is a few layers of computation on top. But very importantly, these layers of computation are not, they don't follow the structure of a grid because we are on a mesh. So this is a two-dimensional structure in a three-dimensional embedding space. And the kind of uniform pixel grid convolution that we are used to for standard convex is no longer appropriate. So what's appropriate is what's called graph convolution. So the structure here is that vertices are nodes in a graph, and then they are connected by edges to neighbors. And there is a feature vector at every vertex. So in the pixel case, it would correspond to sort of all your channels, right? So the channel at a certain pixel. So here these are at a certain node of this graph, which is the graph corresponding to the mesh. And now, what is the convolution operation? What we do is in convolution is we replace the pixel brightness at a point by some weighted average of other pixel brightness values. So something similar here. What's that going to be? Instead of a pixel, we're going to have a node in the graph, and we are going to replace its feature vector by its original feature vector plus some weighted combination of the feature vectors at neighboring nodes. So that's basically what graph convolution is. Okay, and then we can repeat this a few times, and now you've got a cleaned up mesh. And there is a whole infrastructure for this in PyTorch 3D, which you can look up. And if you wanted to do research in this area, build on this, just download that package and you can do this. There's this underlying machinery which you need for differentiable rendering, which is kind of important for this. Okay, so let's see so these just go through the details. Let's just jump there. And what we did was we can take ShapeNet. So ShapeNet is a collection of CAD models. It was put together by some folks at Stanford a few years ago. And it's become sort of the standard data set for learning approaches to 3D, because these are settings where you have the 3D model. So if you want to use supervised learning, you can take those 3D models, render them, you've got images. So now you've got image 3D model pairs, and you can now throw some of your favorite learning architecture, and I showed you one. And basically here are some images, and here are the kind of reconstructions we get. I mean, the point of these examples is to show off that we can deal with varying topology and so on and so forth, and we can do measurements in various, the standard thing which is done is that you have this reconstruction and you compare using chamfer distance and so forth, and yes, and the numbers are good. Now, the original ShapeNet dataset is just these isolated objects. So what we might want to do is to check whether our recovery process will work when we are looking at objects in a real scene, where there's an object and it's in together with many other objects who might be hiding each other, etc., etc. So there, then what do we do about ground truth? So there has been some work where people have tried to guess, take the object like a sofa and try to match it to some IKEA model catalog, and then you have a 3D model for that. So that's what Pix 3D does. So these folks at MIT did this, and we show that we can do the reconstruction in these more complex settings. And this is if you want to show off that your approach is really good. One measure is, does it do a good job on these fine structures, like legs of chairs and so on. Okay, so let's take a summary of where we are right now. So this approach works, okay? I mean, we can scale this up. If we have tons of CAD models for everything, we can do this. But in my view, that's sort of the wrong way to go about things. The supervision is unnatural. We need to have CAD models of the objects we want to reconstruct at training time. And what do we have CAD models for? We have CAD models for objects which are of industrial interest. And that's how, by scraping them, is how ShapeNet was created. But this is not a general approach to 3D in the real world. First of all, I don't like that much supervision anyway. I mean, when their child is growing up and learning about 3D in the world, nobody's injecting CAD models into their head, right? That's simply not what happens. So, and where will you get CAD models for trees and animals and, all the, rocks in the natural world, et cetera, et cetera. So this is something which you can apply for a subset of stuff, right? But maybe for a few objects in a robotic assembly line, yeah, sure. But I don't like this as a general approach. I want a general approach which works for everything. And I don't like the style of supervision. So what I think we need to do is to move to natural supervision. What do I mean by natural supervision? So natural supervision here is the kind of supervision that a kid has when the kid is growing up. So how a kid acquires 3D knowledge of the world is by just going around and getting lots of images. I mean, maybe they see an object from one direction and they walk around and they see it from a different direction. So all that is the way they actually get input. And they have 3D, they have stereo, they can have two eyes, or they can use structure for motion. So somehow that's the signal that they are exploiting to get to their three-dimensional familiarity with the world. Next, I want to note that that once you have that three-dimensional knowledge, then you are no longer hostage to requiring multiple views. So at test time, I can have just a single image. So at test time, even if I have a photograph of a chair, I can guess what the 3D of the chair is, because somewhere in my past life, I built up that 3D knowledge of that shape. So let's see if we can do all this in a deep learning kind of framework. So here's a paper from my group back in ECCV 2018. And this sort of, I think, lays the path for how we should manage with natural supervision. So we decided to take some category for which CAD models are not going to be easy to get by. So these are birds, right? So you have lots of pictures of birds because people like taking pictures of birds. But we don't have CAD models of birds. We don't capture birds and put them in a 3D scanner and scan them and so forth. So we're not going to have ground truth in the nature of meshes for this, right? But we'll have lots of pictures. Somehow to make use of this. In fact, this problem is even harder than the canonical stereo or SFM problem because I only have a single picture of a bird, but I have lots of pictures of lots of different birds. Whereas in the stereo or SFM case, I have multiple views of the same object. Here it's even more general than that. Now, in this setting, how do we recover 3D? So So what we did was we said, okay, I have a picture of a bird. And now I need to help my system a little bit particularly because I'm going to not have multiple views of the same object. So your standard stereo correspondence isn't quite relevant here. So what we want to do is to kind of do a little bit of cheating. We provide some help to the system, and we provide some help to the system by providing key points. So these are the key points that you see here. And these are marked, these are semantic. So beak, tail, etc., etc. And these are marked by humans. Okay, so this is what we do for object recognition. So there's supervision, but it's a little bit of simple 2D supervision, not having meshes. And then you also find have the mask. This is easier to get because there are more generic approaches which will segment out the masks of an object. So given this, that's what we will proceed from that. So here's this bird, and what we are going to do is what's called analysis by synthesis, in the sense that we are going to try to produce that shape which can explain what's in the image. So we're going to take this shape, and that's what we want to get, right? And what we want to do is from the image, we want to guess the shape, the camera, and the texture. And the proof of is this shape, camera, texture good is that it predicts the image. Okay, that's the test, right? And so we are doing this at training time. So at training time, we are going to have lots and lots of images of birds, and we are going to try to guess the shape, camera, and texture. So in this form, it's an ill-posed problem. We'll need to do some regularization, put some constraints. Okay, so this is the idea. If we start from an image, you have an encoder which is trying to guess the camera, which is the pose pi, the shape, and if there's a shape, so the shape is a mesh, and that maps to some key points and some texture. And what we are going to do is we are going to see, okay, does it predict the right stuff? Okay, so there will be some losses. The mask should be what we declared it should be. Okay, the key points should be what they should be, and that the texture should be. And the test here is that it should give rise to the right image. There needs to be some prior. So one prior is bilateral symmetry, right? So the bird is bilaterally symmetric. Others are about smoothness, and there are different ways of modeling that. And that's it. Those are the core ideas, and those enable us to do reconstruction. Now, if you recall, I said we cheated in two ways, right? I want this to just work with this weak natural supervision. You just see objects and that's it. No CAD models, no human intervention. That's what children do. That's what we want to. But we intervened in the previous work. We intervened by specifying those key points, which is essentially providing sparse supervision rather than dense supervision, but sparse supervision, but important one. So what we have done recently is got rid of that requirement. So this is considerable in terms of liberation it provides us. So we call this shape and viewpoints without key points. So this is recent work, and the big thing we got rid of is the need for having key points. No 3D ground shape is needed, no cameras, no key points. And so now we can go to a more general setup. So how do we do this? So the way we need to confront what was the problem we have that we needed the key points for. So it turns out that at training time, you're solving this optimization problem. And that optimization problem, we would do a very bad job of recovering the camera. And it would generally recover some bad camera, and then the shape would be just like some flat shape, like a planar shape. Okay, which of course, from the viewpoint of the one camera, it's perfectly consistent to do that. And then you don't get anywhere. So I'll make an analogy here. In deep learning, we found that even though it's a non-convex problem, in practice, life is not too bad And the reason is because it's over parameterized. So we have that during the course of optimization, you can sort of move around in this space and you get out of bad local minima. So, so here what we do is, instead of trying to guess a single camera, what we do is we try to create a probability distribution over the space of cameras and then alter that probability distribution. So now that's like a nice, smooth, continuous space. So we call this the camera multiplex. So maybe you have like 40 cameras in some discretized version of this. And what you're doing is putting some probability mass on each of the cameras. And over time, hopefully it peaks on one. But it doesn't have to peak on it right away. You are simultaneously adjusting the shape and the camera and the texture. And once you've done that, so this is all at training time. Once you've done that, then you have, now you've got your ground truth, right? Because not pseudo ground truth really, because the system has produced it. And with this, you can train feed forward cameras, and then at test time, everything is just simple. You don't spend a lot of iteration time there. And here are some results from this, and these are as good. So we call this UCMR, unsupervised CMR, whereas the previous one was CMR. And the results are as good, and basically we have got rid of the key point need. So we are now, I think, set for trying to scale up to zillions of categories, because all we need are lots of images. We also need right now the mask, but I think that's going to be that's not so bad a need, because approaches like mask R-CNN, they can give output which is somewhat category agnostic. And some more results. Okay, so now I'm going to switch tacks a little bit and talk about humans. So I talked about objects, and now I'm going to talk about humans. So so this is work with Anju Kanazawa, Michael Black, David Jacobs. Yeah. So what are we trying to do here? So objects, you have to recover 3D shape. For humans, you have an additional complication, which is that, okay, the shape you can characterize by in some parameterized family. So maybe you have like some 10-dimensional space in which, so fat people, thin people, short people, tall people, etc. And that's this beta. But then in addition, you have the pose. So the pose means that every joint. So for example, my elbow, right? I'm stretching this out. So that elbow joint, that has a degree of freedom, and so forth, that elbows, hips, etc., etc. So there's like maybe 80 degrees of freedom there. And then of course you have the camera. So the whole problem becomes that of trying to find these 90 parameters, which the mesh is much more than 90 numbers, but that's because of the constraints of the human body. But what we are trying to do is, for any particular image, we are trying to estimate these 90 parameters with a neural network. What's the challenge? What makes this a non-trivial problem? The challenge is that, again, it's the same problem we saw for objects. We don't have 3D supervision, right? So there we cheated with CAD models. What do we do here? I mean, here for particular humans, how are we going to get their scan? So we can bring them into a lab, put them in a mocap system, capture their shape. Yes, we know how to do this. The graphics people have done this for years. But that's not going to get people in the wild in their real poses, right? Like there's baseball player or tennis player or what have you. So we need some constraint, some prior, and that, so what we'll try to do is to explain the 2D. I mean, we saw that in the object case, but in the distribution defined by the 3D, because some combinations of the 3D shape are not likely, given that you're looking at a human, not a monster. And we will try to capture that from the 3D data that we have captured in the lab. So let's look at the whole paradigm. So we start from an image. This is like a regression problem trying to predict camera, shape, pose. And then there'll be the various losses. It's not so far off from birds. We are trying to project and see whether the key points come out to be right. Aha, but this is the new angle. The new angle is that the reprojection error should be small, but in addition, we should synthesize humans, not monsters. And this discriminator D, which is being trained based on 3D data, that's the one which is going to come in to help us. And here are some results of the kinds of reconstructions we can get. Okay, so this is 2018, and there are now variations, and you could predict parts, and I mean, the technology has got better. Then we moved on from there and said, okay, but we don't just have single images. We actually have video streams. So that gives us some advantages, because obviously the shape is the same and the pose will change, but the pose will change smoothly. We don't want to just generically put in a smoothness prior. The prior of how the pose changes will depend on the activity. If you're running, it'll change more rapidly than if you're walking. Or maybe you are trying to play tennis or bowling or what have you. So this should be learned from data. So we really want to recover 3D human dynamics, right? So we call this HMMR, human mesh and motion recovery. So, so the secret was that we try to do the reconstruction not just as a 3D shape, but as in some kind of 4D space. So the 3D over time. So we can start with images. We can train like this previous encoder, similar to what we did earlier. And now what we have is this representation called a movie strip. And this is a representation over time. It's built up from multiple frames. And that's this big phi T. And how do we train this? We train this representation by it making the right predictions and individual frames. And those could be frames in the past or in the future. So, so that's the idea. So this movie strip is like this intermediate representation. It's that encoding, which we can then decode. Okay, so I'll show you what we can do for this. We can, of course, smooth out motion, but we can also predict future motion, because we can have training data from video strips where we have some where we know what will happen in the future, because in the video clip it's there later on. So what we want to do is to just do that kind of so that becomes a loss for at training time. And then we can essentially run this model to predict the future. So it's a little bit like language models in natural language processing. So you have a sequence of words, and then you try to predict what's the next word that's going to come. And we're trying to do that. And auto-regressive. So you predict one, and then you use that as part of the input, predict the next, et cetera, et cetera. So here's an input video. And then we have so this is where what actually happens. And then this is the prediction of the future. So I have a little video clip here, which goes into the approach.
In this work, we present an approach that takes a video of a person as input and predicts the future 3D mesh sequence of the person. Here, we show the ground truth future video for reference, but the model only sees the input video. To do this, we propose a neural autoregressive prediction model on the latent representation of 3D human motion encoded from the video. This allows seamless transition between conditioning on the past image frames and conditioning on previously generated future predictions. Specifically, for each image frame, we first extract a per image feature vector. From these image features, we learn a latent representation of human dynamics, which we refer to as a movie strip. Each movie strip is causal, which means that it only contains information about the frames up to the current time step in consideration. We then train a 3D regressor that predicts the parameters of the 3D mesh model from the movie strip representation. This is trained with 3D supervision when available. And if not, the model can be trained with 2D key point reprojection loss, along with an adversarial prior to ensure the poses look realistic. In order to predict into the future, we train an autoregressive model, which is a temporal convolutional network that uses the past movie strip representations to predict the next movie strip. This newly predicted movie strip then becomes one of the inputs to the next frame prediction, which may continue repeatedly in succession. From the predicted future movie strip sequences, we can also read out the 3D mesh parameters. This autoregressive model is trained with the same losses, where the predicted 3D mesh model has to match the ground truth 3D or 2D joint labels along with the prior. We also include an additional distillation loss, which guides the autoregressive model to predict the actual movie strip representation. Alternatively, we can also apply the autoregressive model directly on the predicted 3D mesh model. Here, we show some qualitative results. Our approach can predict the future 3D motion of non-periodic actions such as bowling. The yellow mesh is read out directly from the ground truth movie strips, while the blue mesh is the predicted output of our model. Due to computational constraints, we only train our model to predict up to 25 future frames. But in these sequences, we show the predictions are reasonable even past 25 frames.
Okay, and here are some results in a more static sort of a way, but probably the video already made the point, I think, so I'll skip this. And usually whenever there are 3D reconstructions, always you should check from a different camera viewpoint. Let me give you one application of this kind of work. So basically now we have technology for recovering 3D shape and movement in space from just some generic YouTube videos. And one thing you can do for this is help for robotics, because there are lots of instructional videos on the web. And so this is a video of this guy cartwheeling. And from this, we've recovered what a 3D skeleton doing this. And this can be used to train a policy for a robot using reinforcement learning. So what you do is, normally with reinforcement learning, you have a sparse loss at the end, whether you succeeded or failed. Here you now have a dense reward, right? Because at every frame, you are trying to be like what the human was doing at that frame. And since you've trained a policy, you've got a robust system, and this is part of a physical simulation. And turns out it can recover from significant perturbations and deal with disturbances and so on and so forth. So this is, I think, a big area of growth. Imitation learning for robotics. The robotics is hard, and usual RL approaches, they have their sample complexity is way too high. In the meanwhile, the robot will get worn out. So a combination of doing stuff in simulation and imitation, I think, is the way to go. Okay, finally, I'm going to try to bring the two parts of the talk together, what I had in the first part and the second part. And this is also some very recent work, which is trying to perceive 3D human object arrangements from a single image in the wild. So let's put this together. So we've got some capability of recovering humans in 3D. We've got some capability of recovering objects in 3D. But what were we doing? We were doing them all in isolation. Each object was being recovered separately. Every human was being recovered separately. Now this misses out on some very important constraints. So let's look at this image. Okay, so look at it for a bit, and you can imagine a video clip version of it. So these guys bicycling, there's some guy sitting on a bench. Now we can reconstruct here the bench, we can reconstruct the bicycles, we can reconstruct these guys. Okay, that's the input image. Now, there are two interpretations here. Which one of these is more likely? So in the top view, there is this guy who's sitting there, but he's not sitting on the bench. These guys are standing next to their bikes, right? And then there is this interpretation too, which is the one I like better, which is where the object is actually, the person is actually sitting on the bench. The two riders are actually on their bicycles. And the test is, of course, from a different view than how does it look. So this is the second interpretation is the one more likely, and that's what we know because we are familiar with the world we live in, and we have had an opportunity to learn that. So that's what we want to do. We want to not have humans and objects be reconstructed separately, but combined in a way by which we can essentially learn. That's our goal. So how do we do this? So we start from an input image, okay, then find bounding boxes and 3D humans. Okay, you saw some approaches which work for that. Another part is you find the instances, you recover 3D object fit. So you've seen approaches which will work for that. And now what we are trying to do is, this is where our algorithm comes in, which is which we call this predicting human object spatial. So how do we get that? That's what this work is about, predicting human object spatial arrangements. Okay, and then if it's right, then you can look at it from different viewpoints and everything is good. Okay, so let's think a little bit about what constraints would make this possible. Let me give you some examples. So when we do reconstruction from a single image, we always have an ambiguity in scale, right? Because that object, that bicycle could be of a certain size, it could be near us, or it could be far away, right? And a bigger bike. Okay. But humans have a lot of size constraints, right? We know what humans are. Okay, humans are not 6 inches and they are not 60 feet, right? And there's this old quote from Greek times, man is the measure of all things. So the object's size and shape in some sense is defined by the human who's interacting with that object. So that interaction gives us a signal on both, right? Because we know how humans interact with objects. We know the scale of human sizes, etc. So, for example, here's some of the stuff we know. We know what parts of the object. So when somebody is like this guy sitting on the bench, we know what part of his body will be on the bottom of the bench and what part will be on the back of the bench. Similarly, with respect to various objects. So this is the kind of constraints we have, or which we can learn. So I'm not going to go into details here, but basically we want to now do a joint optimization, and that's captured with various of these losses, like is the human object interaction, depth ordering, collision, scale prior on object scale. I'm skipping all the details here. And with that, we can now do reconstructions which capture the spatial layout, the spatial arrangement much better. So here are some results, and you can test them from a new viewpoint. So okay, so that's my last slide. Thank you very much for listening. And I wanted to leave you with the final thoughts, which is that we are in an exciting time because classical techniques from geometry, structure from motion, etc., multi-view geometry, those are being combined with techniques from learning. But how to do the combination is not trivial. I think we started out by just straightforward application of like supervised learning techniques using ShapeNet. But I think what we are getting to now, and we are some fraction of the way on this journey, is natural supervision, the kinds of supervision that human babies have, right? Kids, when they are going around in the world interacting with objects. And that interaction is of the multiple view type. And from that, you build models, which eventually at test time can be used even from a single image. The next point that I made was that we have constraints of time, like human movement. It has some regularities which we can exploit, and then human object interactions have some regularities which we can exploit. And all of these collectively will help us get to a much richer three-dimensional understanding of the world we live in. Thank you very much. I think what the organizers had told me was 45 minutes talk and 15 minutes were questions. So I have ended in 45 minutes, and I'm happy to answer questions.
Thank you. Thanks for your attention to detail. Oops, sorry. Okay. So Thank you for the talk. It's very inspiring about, especially at the last part, like how we can extract those special arrangements due to some priors that we already know and can't change, like the human shapes and size, etc. So I will go to the Zoom and YouTube links and pose the questions from there. So from YouTube, Marco Agus says, thank you for the really inspiring talk. And the question, his question is it possible to use human measure to help for full 3D reconstruction of indoor environments?
So yes, so certainly when humans are around in a 3D space, like chairs, tables, beds, right? So we can get, they're providing a signal, right? The size of a chair is related to the size of a human's bottom, for example. So yes, that gives us some approximate signal. But it's going to be approximate. Let's keep that in mind, right? Because all humans are not of exactly the same size. I can use the human as an approximate ruler, not as an exact ruler. So long as we keep that in mind, I think it helps. For some purposes, people really want exact 3D reconstruction accurate to a millimeter. If so, then you have to use different techniques. At that point, your classic stereo techniques, multi-view geometry techniques, or active sensing techniques with LiDAR, RGBD, so those have to come in. But I'm arguing that most of the time we don't need that kind of accurate shape, that millimeter accurate shape. We need approximate shape, approximate layout. And for that, the techniques that I've described are good. They're not good for that 1 millimeter shape accuracy. I think the classical photogrammetry, SFM, I mean, that's the way to go for that.
Okay, thank you for the answer. Another question from Alexei Artemov, which is one of the organizers of this workshop too. His question is, compared to stronger priors and templates, can differentiable rendering for meshes be regarded a more advanced or complex or a simpler component for 3D reconstruction methods?
So I'm a great believer in differentiable rendering. I think that this is effectively what it has done is it's enabled us to address the inverse problem. Okay, so let me back out a little bit and answer maybe a broader question. And the broader question is, always the area of 3D geometry has always been based on having a forward model and an inverse model, right? We are trying to guess a 3D shape, which we judge by reprojection error. We predict some key points and then we see what's the error between predicted and actual. And then it takes some difference and square, and then there's some loss function. So the classic bundle adjustment of structure from motion going back 20 years. But what that did was it only looked at locations. So the loss was only in xi, yi coordinates, right? But actually we can aim to have more, there is more signal in the image, because pixels don't just have a location, they also have a brightness value, which is what we should be exploiting. So your classical bundle adjustment techniques from structure from motion, they were not making use of the brightness values in that sense, right? That was being cast aside. It was just at the end recovered as a texture map. So the differentiable rendering technique throws everything into the machine, and we are trying to get it all to work. And of course, I mean, the needs of deep learning are that you need to be able to calculate gradients and then do SGD and so forth. So differentiable rendering just takes, it's like the moral counterpart of bundle adjustment, but it's better. It's better because it has it has the geometrical loss implicitly, but it is capturing in the loss at the level of pixel brightness values. So in the old days, there were these techniques which were called direct approaches, which were that instead of first computing correspondence and then estimating and then using the correspondences in the geometry direction, you try to work directly with the image brightnesses. There's work from Horn going back to the 1980s like that. Those approaches didn't take off because they used to get stuck, and the local minima problem was bad, and so forth. But I think that differentiable rendering is essentially like a machinery which is enabling us to tackle that. So I'm a fan. I think how it's going to get used over time, since it's fairly early days. I mean, we have some use of that in the papers that I described. I didn't talk about it much, but it was being used in all the approaches I described, and I think that it's going to be. We'll figure out in the next year or two how to exploit it as well.
Thank you. The next question from Aditya Balu. Thanks for the great talk. I had a question about the possible contradictions in the loss priors we impose and the data we have. Specific example is, what if we impose symmetry constraints, but most of the data we have doesn't have symmetry?
Yeah, I mean, that's a standard problem, which is we impose some constraint which is not true, right? So this is like always the dilemma for all of learning approaches. Learning can't be done if we don't impose some inductive bias. Inductive bias is helpful for learning. If you impose the wrong inductive bias, you get into trouble. Okay, so what do we need? We need, if you have tons and tons of infinite amounts of data, you can throw away most of the inductive bias and priors. But in practice, we have found that there are some intermediate positions which are good, right? So convolutional nets, that itself has an inductive bias, which is that it's shift invariant. So the processing is the same everywhere in the image. Now, actually, it's not quite true, right? In fact, in human vision, we don't regard the upper part of the visual field and the lower part of the visual field as the same, because upper part of the visual field, you have the blue sky, and the lower part of the visual field is where you have the ground. And so the statistics of objects are different. But fine, we ignore that and we do very well with this convolutional assumption. So symmetry, back to symmetry. So I think symmetry is a pretty useful assumption for lots of biological shapes, but it will be wrong sometimes. And even human shapes, human faces are not exactly symmetric. So what we can try to do is to have one level of learning above this, which is to know when to impose the symmetry constraint. So so that's like a meta learning problem, if you will, if you want to use fancy terminology, because we should know where we can impose that symmetry constraint. And right now we're just imposing it. Ideally, we should learn when we can impose it. So we'll impose it for some kinds of animals, but we won't impose it for rocks, for example.
Yeah, and also I think the question was more about the contradiction in the when we are posing those priors versus the data actually not having them, so that we actually base our assumptions on different properties of the data that it doesn't.
Yeah, no, so that is dealt with always by optimization. In any optimization framework, be it neural networks, be it pre-neural networks, you have various terms, and then there's a loss, and then these terms have some coefficients, and then the system will find a solution which trades them off. So that's how it's being dealt with practically, but I was responding to it more philosophically. Yeah.
Sure. The next question is from Bernard Egger. In the work of Blanz and Vetter, morphable model for faces SIGGRAPH 99, they actually use a differentiable renderer and stochastic gradient descent for optimization. So what is the actual big difference now, except that we can now use data to ease the inference?
Yeah, I mean, differentiable loss functions, okay, of course, those have been around for a while. It's the setup is in the context of neural networks, right? So basically, neural networks, given the technology that exists now in 2020, with the various architectures of, ResNet and UNet, and we have, the community has over time found lots of good neural network architectures, right? And we are combining that with ideas from optimization. So it's really the whole combination. None of these things is ever completely new. They always go back. We can always trace for every idea some antecedents in previous work. But nevertheless, I still regard differentiable rendering as a contribution. I think it builds on previous ideas, of course.
Now I'm switching to YouTube questions a little bit. So from Ashish Tawari, the question is, you mentioned that toddlers are now fed with CAT model, but they interact and learn. How important is having the stereo eyes for toddler in this way of learning 3D with images?
Good question. So I think humans get, so we get 3D in a couple of different ways. For one is two eyes, right? So stereo becomes effective like maybe 3 months or 6 months in, and then that's giving you some depth signal. But stereo works only nearby, right? So the accuracy of, so the error in stereo scales as the square of distance. So objects which are far away, like more than 10, 20 feet away, stereo is not effective. Okay, the other way you get 3D information is by by actively manipulating an object. So the child, the baby girl has some toy in her hand, and then she moves the toy and looks at it from different directions. So by moving the object, you're getting multiple views. Okay, so this is interaction, and this is the best kind of data you can have because you can choose the views. And then you get some data when you start to walk. So when I walk around, then it's like more like classic structure for motion. So it's really three different things. There is binocular stereo, which is effective in the near field. There is interaction, which is obviously in the near field because only objects in your hands that you can manipulate, by which you can rearrange, you can get different views. And then there's structure from motion, which comes from walking around in a space. And all of these together help us. And there are people who are stereo blind. So approximately a few percentage of the population is stereo blind, and they can't do the correspondence between their two eyes, but they still have the signal coming from structure from motion. So that's, I think, very powerful. So it's all of these are used together. We don't use CAD models. That's what we don't have.
Next question from Ajinkya Delgade. I'm sorry about the pronunciation. Great talk, very inspiring. Could you comment on how would we represent different entities like humans, objects for simulating real-world scenarios?
So, okay, so objects, I mean, there are like there's the standard three ways of representing them: as voxels, as point clouds, as meshes, right? So these are the graphics people, of course, love meshes. Point clouds is what the SFM people love. And voxels is what were loved in the early days of deep learning and 3D. So what's the future? I think it'll always be, it's not just one or the other, but people will move around between these three representations, I think. I like meshes personally, because I think with meshes, then you can just use the graphics pipeline. Point clouds are a bit of a pain.
Graphs are like an intermediate representation, both for points and meshes and maybe even voxels in different sampling.
Well taken. Humans are more of a more tricky because humans are non-rigid, right? So what we are seeing right now are, I mean, the work that I described was all using the simple model, SMPL, from Michael Black's group. So that's like a mesh model, and it's been constructed first from data. And now what it does is it conveniently makes it a finite dimensional problem. So in terms of optimization, you start from that shape, and we can say that this key point, like the elbow, is here, etc., etc. But will people be completely happy with that forever? No, I think not, because if you talk to biomechanics people, they're not super happy with a model like that, because to them this looks a little bit too robotic-y. Whereas humans are, we have skin and muscle, and it's sort of more soft and smooth, and I think this model is just is not, for certain biomechanics purposes, it's not going to be good enough. And I mean, obviously we need some augmentation just for dealing with face and hands, but people are doing that. But I'm just saying at some point we'll hit into the limits of this. But right now, what I felt was that at this time, given the kind of image resolution that we have, we get a lot of mileage out of this model. And I want to state a philosophical thing. The problems that I talked about today largely they were all in the setting of low fidelity reconstructions. I'm not trying to focus on the 1 millimeter accurate reconstruction. Okay, so these approximations are good enough for my purposes. There will be settings where you want very much more subtlety, much more detail, and then we'll see problems here.
Yeah, I also think that those are like abstractions that make us progress towards like extracting something from what the data we have. But the more the needs will develop, the more elaborate the representations will also emerge. I will use my force right now and add a question of mine in between.
Of
So
course.
my question is actually about those representations. So what about the learned representations being interpretable, like in a way that they are still learned and they are not based on a specific prior that we depend on, but we can learn the rules and the hierarchy and even maybe the granularity problem to solve the granularity problem, the scale of each of the parts, or like the hierarchy from the data itself, like a procedural model, not only for humans, but for most of the domains, like a procedural model, but it is learned in a deep learning setting with interpretable modules.
Yes. So the big question is essentially about procedural models of objects and so on. And yeah, I think that needs to be pursued, and it has some advantages, right? So the advantages always are that if you have if you have clever prior knowledge, that means you will need less data, right? And it'll be more interpretable. So I think that is of value. I think the one or two papers from my group which have been about trying to Shubham Tulsiani is the first author on trying to use volumetric primitives and trying to model objects like chairs. See, like a chair, you can think of a chair as a mesh, or we can describe a chair as 4 legs, a seat, and a back. And somehow that seems slightly more satisfying, right? And because then you can create many new chairs easily because you just modify some parameters. So I do see some value in those models. I think the challenge is these two worlds currently don't play well together,
Yeah,
right? So there's a discrete parts kind of world and this more continuous world, and we are essentially, this is our research, right? We are trying to find ways of making them work together, and let's hope we will succeed.
I hope so too. So I'm going back to questions in the Zoom chat. From John Bednarik, question is, which of the 3D shape representations, meshes, implicit functions, parametric mapping, atlases, voxelized representations, etc., do you think will succeed in the future as the most useful for 3D shape representation, or perhaps a combination of those? You partially already answered this question, but I wanted to pose this as it was already
Yeah, I think, as I said, everything is useful. I think voxels to me seem dated. Like those are the ones which probably are ones I would think they are in the past, less useful in the future. Implicit functions are active. I think meshes are active. I think point clouds have some value. Like I was ready to give up on them, but there is some recent work from actually Georgia Gioxari, Olivia Wiles, and so on, the SynSyn work, which makes very nice use of point clouds. Because with point clouds, there's the issue of the order of the points, and so on. So I think currently I would not kill anything. I would just say let's make progress.
Okay. The next question is from Evgeny Bernev, which is also one of the organizers of the workshop. So we impose various losses and learn 3D shape. Do we also need to learn first some 3D generative model and use it as additional constraint when recovering 3D shape?
in a sense, the human work I think of as being a generative model, right? I mean, it has like these 80 parameters, and by tweaking those parameters, I can get different human shapes. So that is a generative model. I think for objects, no, we didn't. We had an approach which is analysis by synthesis, which is in a way a bit more rich than what people do when they're just doing COCO style object detection or classification, because there you just get, like chair, very little output. Here we get much richer output. But I think, I think more is needed here. And let me say what is needed here. What we are doing is we are just stopping as soon as we produce the object. We want to do things with the objects, right? So the objects are entities in themselves. And in a way, generative models enable us to regard the objects as like first class, and we can rearrange them and we can do various stuff like that, right? That's the power we need. We don't want to stop by just saying, okay, object. No, you want to now think of these objects as elements in some representation. Now, at that point, I think we have to move out of this ConNet structure. We need something else for moving these objects around. I mean, classical graphics has tools for moving these objects around. I mean, scene graphs and so on. So it's not that there isn't a way to deal with them, but always the challenge is here is a line of work and a style of reasoning, and here's another line of work and a style of reasoning. How do we make them play nicely together, right? And that's where the research problems are. I think in due course, I mean, this area of 3D learning in 3D, I mean, people in my students and postdocs and we have been working on this from like 2015, and always the goal has been, how do we synthesize these lines of thinking from different traditions? And I think there's just more to be done.
So we are a little bit out of time, but if you also have time, Professor Malik, I can take a couple more questions.
Sure.
So the next question from YouTube is, really great talk. Do you think these methods could work on non-symmetric shapes? For example, if you see the back of a car, it would be able to predict the front. I think you answered this question a little bit before, so I'm skipping this one. And the YouTube stream is a little bit delayed from our Zoom meeting, so that may be why. So the next question is, there are several simple-based methods, SMPL-based methods to reconstruct 3D human models, but how different is it from reconstructing texture? For example, reconstructing side view clothing texture for a human.
So I think in the context of human recovering texture, I mean, effectively, this comes down to the question of recovering clothing, right? And clothing is more complicated than recovering texture for an object or a bird, because clothing is flexible and deformable and so on and so forth. So yeah, that's a pretty challenging problem, and I haven't worked on that, so I don't have anything to say.
Okay. And after that, for the 3D for the representations question, I think there's a follow-up as why not neural scene representations instead of those handcrafted representations?
Neural scene representations, is this reference to the work from DeepMind and so on?
The NeurIPS work from Sitzman et al., the 3D scene representations?
Yeah, I mean, I think okay, got it. Yeah, that's possible. I mean, I'm not excluding anything, but I'm not fully convinced yet about a particular track yet. Yeah.
Okay. Going to last two questions. Do you think that Henry M. Clever asks, do you think that exploring a different parameterization of the human model would help to make human models more amenable to learning differentiation? For example, using Euler angles instead of axis angle joints, or body shape with 50 PCA parameters rather than 10.
Yeah, but I think that one could, but I don't think there's a big mileage there, because that's still minor variations on the theme. And the people who worked on simple, they already spent a fair amount of time getting to a sweet spot in terms of what's the right. There's always diminishing returns. You have more and more parameters, and it's more of a challenge to estimate them from data. I think the places where simple needs to be worked on most is faces and hands, right? And there's something called simple X. So
Yeah.
the face, I mean, simple, it's just nothing, right? Hands, both of these, face and hands, are very important. So I would say the place, the area to work on with respect to augmenting simple is faces and hands.
Actually, there is a extension of simple to faces called flame model, and flame is fitting the faces very like a more detailed way in a compatible simple version. That is extension for the faces. So check out the flame model for that.
Yeah.
Okay, last question. How Kang asks from the YouTube channel that in the mesh R-CNN work, the results are compared on their point cloud metrics. Can the PCD metrics reflect triangular mesh features well? Why not directly use triangular mesh, if any? Thanks.
Okay, because the mesh as such is arbitrary, right? Because there could be different meshes which are approximately the same shape. So I would say that comparing at the level of point clouds is neutral territory. I think that, and of course, if you make the point cloud dense enough, it is as accurate a representation of the underlying mesh as possible. So the idea is you get to the point cloud because it's neutral territory. And in this neutral territory, we can compare meshes. We can compare meshes to point clouds, meshes to voxels, anything. I think it's nice to have a representation which is neutral.
Okay, thank you. That concludes all the questions. Sorry, I am so happy that this is online, that we have so many questions. Maybe in the workshop that we were face-to-face, there wouldn't be that many questions. So I'm really happy. And thank you for your patience, and thanks for 12 minutes overtime. So I hope you enjoyed the workshop, everyone, in the Zoom link. And thank you, Professor Malik. For your contributions.
Thank you for inviting me. It's been a pleasure, and I've enjoyed the interaction.
Thank you. Us too, all of us.
Bye-bye.
Bye.